Let me begin by thanking you for your interest in attending our talk today from the whole team at United Silicon Carbide. My name is Pete Losey. I'm the Director of Technology Development. In this presentation, we'll focus on how to achieve optimal performance with silicon carbide FETs by minimizing both EMI and switching losses. First, we'll provide a very short introduction into our United Silicon Carbide FETs. We'll discuss the benefits of switching fast with Kelvin source connected packages, like the TO247 4-lead, the D2PAK 7-lead, and a DFN 8x8, all of which are gaining in popularity across wide bandgap applications. We'll dive into how to manage these waveforms, focusing on the fast turn-off of these devices. We'll investigate common approaches of slowing the devices down with external gate resistance versus use of small device numbers. Finally, we'll refer you to expanded resources on these and other topics about how to get the most out of silicon carbide switches. It's important to start with the motivation behind this discussion. Fueled by the demand for high efficiency, high power density, system simplicity, and reduced part count, silicon carbide could be described as a designer's dream. This is due to their ever-reducing RDS(on) and low conduction losses, especially at light load. They switch incredibly fast, being single carrier devices even at high voltage, allowing simple, efficient systems. However, practical design constraints must be employed to avoid the introduction of silicon carbide from becoming a nightmare. Managing EMI and well-behaved switching waveforms must be done by slowing down the voltage and current transitions to a stable state with minimal overshoots. The proper package should be used to ensure small parasitic inductances and avoid ringing on the gate. Compact PCB layouts need to be implemented, in so much as voltage clearance and safety regulations would allow. And where applicable, downstream filter design should be employed to mitigate the impacts of EMI generated by these fast switching devices. United Silicon Carbide offers a wide range of silicon carbide components to meet the needs of a variety of applications. We offer 650 volt to 1700 volt Schottky diodes, 650 volt to 1700 volt standalone depletion mode JFETs, and silicon carbide normally off FETs at 650 volt and 1200 volt. Unlike conventional MOSFETs, our switch technology is based on co-packaged silicon carbide JFETs and a cascode optimized silicon MOSFET. This forms a high-performance, easy-to-use, normally off FET. These parts work well with standard gate drives and offer ultra-low RDS(on). Our 7 milliohm 650 volt and 9 milliohm 1200 volt rated discrete FETs, offered in TO247s, are the lowest on-resistance parts on the market today. The FETs have an excellent body diode with low forward voltage drop, excellent reverse recovery that's stable across temperature. They can be driven with any silicon or silicon carbide gate drive voltage. They have a built-in ESD protection in the gate and are rated to TJ max of 175C. The FETs have a full 5 volt threshold voltage, which along with the small reverse transfer capacitance gives good threshold noise immunity even when using VGS off of 0 volts. Since the low voltage silicon MOSFET control switch dictates the transfer IV characteristics, the parts are fully enhanced at 10 volt gate drive, so 12 volt gate drive works well, especially in ZVS applications. The parts are compatible with silicon superjunction, silicon IGBT, or silicon carbide MOSFET existing gate drive voltages. In this slide, I'd like to briefly show the benefit of using Kelvin source connected packages like the TO247 4-lead. By overcoming the common source inductance of the source power lead, these packages can yield much faster switching transitions while keeping the gate waveforms clean. In the inset here, I show the reduction of the induced spikes seen on the gate when switching our 40 milliohm 1200 volt cascode under high current. Note the smoother waveforms and absence of spikes with the 4-lead part shown in the solid blue lines. The TO247 4-lead will be the focus of the results shown in the rest of this talk. Here we're showing the example of a high current fast turn-off waveform with a silicon carbide MOSFET. The device is switched off from 50 amps to 800 volt bus. This is done with minimal external gate resistance. The device is switched from VGS on of 18 volts to 0 volts in the off state. The VDS peak extends to almost 300 volts above the bus voltage, and the long duration high frequency ringing will introduce EMI into the system. Our aim is to minimize this peak and dampen the turn-off oscillations while cleaning the gate waveforms, all while minimizing the impact on switching losses. Let's consider the simple half-bridge clamped inductive switching turn-off shown in this slide. The left side depicts the low side device being on and the high side device being off. The current is initially flowing through the bus capacitor C, the load inductor L, and the parasitic inductances L1, L2. When we turn off the low side switch, the current commutates to the freewheeling device in the high side, and parasitic inductance L1, L2 will see a negative dIdt. This leads to voltage being induced VL1, VL2. If we represent VL as the total voltage across the parasitic inductances in the loop, then the drain source voltage of the low side device will be equal to the bus voltage plus the induced voltages across the parasitic inductances in the loop, shown with the red arrow. If we look at this simple equation, we can see that one possible solution to the problem is slowing down the dIdt and dVdt by using a higher RG off, and thus a trade-off exists between the VDS waveform and efficiency. Alternatively, we can reduce the low power loop stray inductance. While this is important, it's constrained, as I mentioned previously, and it'll be outside the scope of this talk. We can also use smaller, lower inductance surface mount components, but this often comes at the cost of worsened thermal performance. One can also employ just a simple RC device snubber to relieve these constraints. In the next few slides, let's compare these two approaches using both silicon carbide MOSFETs and united SiC FETs. To evaluate these approaches, we'll use double pulse switching of a half bridge with an inductive load. The devices we use are 1200 volt 40 milliohm silicon carbide FETs packaged in TO247 4-lead. The current transformer here will measure both the device and snubber current. The table summarizes the conditions we use. In the first case, we'll switch to silicon carbide MOSFET very fast, using no external gate resistance, and this will be able to illustrate the overshoot in EMI that we'd like to mitigate. In the second case, we increase the external gate resistance to 5 ohms on and 5 ohms off in order to improve the switching waveforms. For the third case, we'll keep the external gate resistance during turnoff to 0, but introduce a small 10 ohm 200 picofarad device number. We'll then repeat this exercise with our united SiC UF3C series 40 milliohm 1200 volt FETs. This will help us to show that using a device number is a general solution for silicon carbide devices. For the fastest case with no added external gate resistance, we can see a turn-off VDS spike of over 1050 volts and a turn-off ringing duration of about 104 nanoseconds. During the turn-on, the large current overshoot and large recovery dIdt induces a gate voltage underspike, despite this part being packaged in a 4-lead TO247. Increasing both RG on and RG off to 5 ohms, we can see the peak voltage overshoot can be reduced here to 1000 volts, but the duration of the voltage ringing remains largely unchanged. You can also see the longer turn-off delay stemming from the RG off. Looking on the right to turn on, the higher RG on shows a much smoother waveform and reduced current overshoot during turn on. Now, we've again removed the external RG off, but placed a small 10 ohm 200 picofarad device snubber across the switch. We've left the 5 ohm RG-on in place to maintain the smooth turn-on waveforms. You can see with the turn-off waveform on the left that the peak voltage has again been reduced to 1000 volts, but now the ringing duration has been reduced to 33 nanoseconds from 104 nanoseconds. So the snubber is more effective at reducing both the peak overshoot and the turn-off ringing. There is also no extra delay time induced with this approach. There is a slight increase in IRR during turn-on, modestly increasing from 94 to 97 amps. So putting both the snubbered turn-off and the one with the external RG off side by side, we can see the same turn-off peak voltage is achieved, but the improvement in the damping and lower turn-off delay time is clear with the snubbered approach on the left. Let's look at the switching losses measured across load current with the different approaches. The turn-off losses are shown on the left. In this plot, the green curve represents the losses when no external gate resistance nor device snubber was applied. Recall that this condition suffered from excessive ringing on both the drain and gates. The blue curve represents the turn-off losses when the device switching was tuned with the external gate resistance, which did control the VDS peak to the same value as the snubbered approach, but it did not reduce the duration of the ringing. Note here that the E-off losses at 48 amps more than doubled compared to the no external RG case. The yellow curve represents the turn-off losses of the device when applying the device snubber, while still using no external RG off. The snubber is more efficient in turn-off because it allows faster switching, while maintaining the low voltage peak and reducing the duration of the ringing. The curve on the right shows turn-on losses when the RG-on is 5 ohms. This is done with and without snubber. Note here that there is a slight increase of E-on due to the presence of the device snubber. So, let's consider the total switching loss of E-on plus E-off. Here we can see that the snubbered approach is more efficient above about 18 amps. At a nominal rating of 39 amps for this part, and assuming a switching frequency of about 40 kilohertz, this would result in about 10 to 11 watts of savings. Meanwhile, the snubbered approach resulted in cleaner waveforms and shorter delay times. Now, let's see how well this same technique works with United Silicon Carbide's UF3C 1200 volt 40 milliohm devices. We switch these fast devices here with no snubber from 45 amps to 800 volts. You can see the turn-off shows large VDS spikes and long duration ringing, just as the case with the no external RG of the silicon carbide MOSFET. The turn-on shown on the right has a smooth waveform with proper selection of RG-on equal to about 30 ohms. Now, we repeat the benefits of the device snubber by applying a 10 ohm 200 picofarad device snubber across the switch. We again see the reduction of the peak VDS to the same 1000 volts and the well-damped short duration ringing. The snubber has almost no effect to the turn-on waveforms shown on the right. Let's have a look at similarly rated silicon carbide FET's turn-off waveforms now when placed side by side. You can see both exhibit well-behaved waveforms, as expected since the snubber dominates the turn-on. Note here that the device's dual source compatibility is improved when using this optimization approach. In this plot, we're overlaying the total switching loss of each of the cases measured. In the yellow curve, the silicon carbide MOSFET's snubber optimized switching loss versus load current is shown. The dark blue curve shows the United Silicon Carbide's 40 milliohm device switching loss versus load current when similarly optimized using the 10 ohm 200 picofarad device snubber. Clearly, the use of device snubbers are an effective way to optimize the switching of both types of these devices. The United Silicon Carbide device, shown here, exhibited lower turn-off and lower turn-on losses and was found to be more efficient across the ranges studied here. For the sake of brevity, I will point you to our design resource pages at unitedsic.com, where you can find the physical explanations for why the snubber offers a superior performance trade-off. However, it is important here to point out that the losses in the snubber are quite low and can be handled well by surface mount components. There's a common misconception that the snubber resistor experiences the full CV² energy shown in the gray bars on this figure. This assumes that all the energy is dissipated into the resistor. The blue bars, however, show the measured resistor loss in the snubber used in this study. The energy difference between the CV² loss and the measured resistor loss is dissipated in the device during turn-on transition and is indicated in the orange bars on the graph. To visualize this, the diagrams on the right depict the current flow during the switching transitions. At turn-off, the snubber capacitor charging current flows into the snubber resistor, generating an I²R loss. This charging is not a constant voltage charging. During turn-off, the snubber cap voltage is more like the device voltage with a linear dV/dt, resulting in close to constant current charging. The result is that the snubber resistor loss is much less than the 1/2 CV². At turn-on, the device channel resistance and the device snubber resistance are in series to discharge the snubber cap. Here, the device channel is in the active regime with a high impedance, and in fact, most of the snubber energy is dissipated in the device instead of the snubber resistor. Under an example condition of 40 amps and 40 kilohertz, the snubber resistor loss is only about 0.8 watts. This is easily handled by 1.5 watt thick film resistors, or you can put two in parallel to further improve the rating margin. In summary, we've demonstrated that a small RC device snubber is a more effective and efficient way to shape the silicon carbide switch turn-off waveforms than simply tuning using an external RG-off. In light of this, device snubbers are recommended for most silicon carbide designs. Snubbering can also improve device dual source compatibility. So, we recommend designers to optimize efficiency by managing waveforms while minimizing switching losses, employing device snubbers to fast parts, and using United Silicon Carbide's UF3C parts in Kelvin source connected discrete packages. I'd like to close today by just referring you to our design support resources, our general guides and tips for how to best use United Silicon Carbide FETs.